Okay, I'm gonna introduce the Lagrangian dual problem. And I'm gonna explain why it obeys weak duality. Oh, Jesus. Okay, there we go. Okay, so what we're gonna do is, usually we have an unconstrained optimization problem. And now we want to solve constrained optimization problems. In this case, it's gonna be minimization problems, okay? So for example, usually we have minimize f of x, okay, for the variable x. So here we might have, I don't know, we have the level curves, or the level sets. So for example, f of x might be 0 here, and then plus 1 here, and then plus 2 here, but maybe it's minus 1 here, and our minimum would be here, okay? This is an unconstrained optimization problem. Now we have problems that are a bit harder, which is minimize f of x, where subject to x belonging in omega. So maybe we have a problem like the above. Let's just copy it. Okay. But maybe it must be restricted to some weird function or whatever, some weird set. Okay. So here, the minimum will probably be this guy over here. That's the minimizer. And the minimum would be attained at the minimizer, of course. Okay, so that's what constraint optimization means. We're basically trying to find, another way of writing this is find the minimum for x belonging in omega, the minimum of f of x. And the set that we restrict x to is called a feasible set. Okay, this over here is just another way of writing the same thing, pretty much. So I'm gonna put it over here. It's not very important. Okay. Now, remember, unconstrained optimization problems are very simple. These are complicated. But there's a simple way to turn a constrained optimization problem into an unconstrained optimization problem. Okay. Let me explain. There we go. So the way we turn this problem, which is constrained, into an unconstrained problem is very simple. So low values are good. We're trying to find the best value. Okay. So the way to make sure that the best value is inside the region is to make the values outside the region bad. Okay. What's the worst case? Well, let's just make them infinity. Okay. So all the values outside of the region, this is our region, by the way. This is a boundary, sorry. This is the boundary of our region. And this is our region over here. So now that outside everything is infinity, this is awful. There's no point going outside. Okay, so the minimum of the problem will be inside, where the problem will be not too negative, not too positive. It certainly won't be plus infinity. So the minimum is assured to be inside the region. So this constraint problem above is going to be equivalent to minimize for the variable x, f of x plus p of x, where where we're going to say that p of x equals the worst, really bad, outside, for x outside the feasible set, it's going to be, it's going to be plus infinity. For x inside, it's going to be 0, so it won't change anything. Okay, these two problems are equivalent. The Lagrangian problem is going to be a similar thing, not too different. Instead of penalizing by infinity, we're just going to penalize it more smoothly. Okay, imagine our problem is given in this form instead. Minimize f of x subject to some constraint to x such that c of x is smaller than 0. Okay, where c is the constraint. Here we're not going to have equality constraints, we just have inequality constraints. So here our set of feasible points is going to be x such that c of x is smaller than 0. Apologize for the size here. So the c of x is negative. Okay, now before, what did we do? Let's try to look at the case we had. Yep, I am recording. Let's try to look at the case we had before. Okay, before we had, like, let's make it clear where it ends. Okay, these are the boundary of our region. Okay, so before we had like plus infinity outside of the region, right? Now let's just have instead positive values. Add something positive outside, add something negative inside. We already have something that looks like this, right? We already have a penalization function that looks like this, which is c. Okay, so this problem is similar, not quite equivalent, similar to minimize f of x plus a certain penalty function, but instead of the other weird penalty function, we're just going to add c of x. Okay, because the best values are the low values. Okay, so the outside value, we make the outside bad by making them positive. Okay, so outside this is positive, so the function is going to be more positive, so it's going to be worse. And inside this is going to be negative, so the function is going to be better. Okay, more negative, more lower, so it's going to be better. Okay, so this is similar to this problem is similar to that one, but it's a bit arbitrary to have c of x here actually, so we multiply it by a scalar, because it's a bit arbitrary to just, because for example this restraint is equivalent to this restraint, right? Because if cx is negative, so is 3cx. Okay, so these problems are similar, and we're going to demand that lambda is positive. Okay, and we're going to rewrite it in this way. I'm just going to rewrite it. This function, which is f of x plus a penalty, is going to be equal to L of x lambda. Okay, this is called the Lagrangian. This is what Lagrangian is. Lagrangian is just the objective function, which is f, plus a penalty. Okay, so I mean, obviously, the points inside are going to be favored. So for example, if lambda was plus infinity, the minimum obtained would always be inside. In fact, the solution to our original problem, which is the problem that we care about, this one, the solution, so the minimum, the solution to the new problem is never going to be above it. Okay, so we know that it's at least better. The solution to this problem is at least better than the initial problem. Okay, so let's call the solution to this problem, let's call it g of lambda. G of lambda is equal to minimum of x of the Lagrangian. Okay, and the cool thing is that the dual function, this is going to be the dual function. G is the dual function. Okay, dual function. We know that this function is only going to give values lower than our solution. So our solution is minimum x belonging to the region, belonging to the feasible set. We're looking for this minimum. This minimum is going to be the solution to our problem. But f of x, let me put it this way. I'm just claiming that the solution found of our new problem here, this one, which is not quite, which is, I don't know if it has a name, but that the solution found here is smaller than the solution, the minimum that was being asked initially. This is what we're actually interested in, okay, solving this problem. So I'm just claiming that the minimum found is going to be smaller than the actual minimum. Why? Well, because the actual minimum, remember, this is equal to minimum. Sorry, I meant this is the problem that we're trying to solve. Okay. The solution of the auxiliary problem is going to be smaller than the solution of the actual problem that we're interested in. Why? Well, this is the solution that we look for. Now, we're going to obtain, let's say, an even better minimum if we subtract it by a negative number, right? Or if we add a negative number. Okay. And that's precisely going to be lambda. Remember that L. Remember that if x is in the feasible set, then the Lagrangian is going to be smaller than f of x. Okay. So the minimum of f of x is going to be greater than the minimum of the Lagrangian. Okay. And the minimum of the Lagrangian. So the minimum in a region, of a small region, is obviously going to be smaller than the minimum in the whole region. Okay. Why? I think this is obvious, but for example, imagine that the minimum outside is here and the minimum inside is here. Okay. This would be our function. Maybe this is the feasible region. Here, this is the feasible region. Well, Well, if the minimum of the inside region was smaller than the minimum in the whole region, so imagine that instead we would have this, then the minimum on the inside here would be the minimum of the whole region, obviously. Okay? So it doesn't make sense that the minimum of the whole region has to be smaller. Then we have more options. So the best option has to be better, obviously. That's a good way to put it. Okay? And what is this function? Well, this is precisely equal to g of lambda. Okay? This is not a problem, this is just a statement. But we proved what we wanted to prove. Okay? Okay, so an important thing I proved is, given a constrained optimization problem, we can go to an auxiliary problem involving Lagrangians. So we can call it the Lagrangian auxiliary problem, name that I just made up. But this one will give you solutions that are at least better than this one. Okay? So they're at least better. They can't be worse. So they're lower bounds of the initial problem. Now, finding lower bounds is pretty good. Why? Because, for example, we're trying to find the minimum. Maybe the minimum is here, the minimum of the original problem. And we're finding lower bounds, for example, here. Well, possibly, if we find the highest lower bound, then we would find the solution itself. Okay? So let's try to find the highest lower bound. And that is, the highest lower bound is going to be simply the maximum of g lambda, subject to. So this is a very simple constraint, okay? So it's not hard at all. So now we have this problem. This is the dual problem. Okay? And if we find, and this is going to give us the best lower bound that we can of the lower bounds that this gives us. It's going to give us the one that is closest to the actual minimum. Okay? Remember that g of lambda is smaller than the minimum we're looking for, the solution. So the maximum of g lambda is obviously going to be also smaller than the minimum, but hopefully not so small. Lambda is greater than 0 because remember that's we have always assumed that lambda was greater than 0. Okay, when I was talking here, we have always, otherwise it doesn't work. Okay, the penalty has to make the function better, it can't make it worse, otherwise none of this works. Okay, and this problem is a dual problem, and if you notice, this is the solution to the dual problem. So the minimum, this is solution to dual problem, and this minimum is going to be solution to the initial problem, which you call the primal problem. Okay, this is weak duality. Weak duality allows us to obtain lower bounds to the primal problem. It says that solution of dual is smaller than solution of primal, which is always true in the way that we've done it. Now it's weak because the best case would be where this is as high as it's going to be. It's really high. It's actually equal. Strong duality is when the solution of the dual actually is equal to the solution of the primal. This, for the Lagrangian problem, this is always true. Not always true. This is not always true. Okay? However, I could prove it, but there are plenty of conditions that we can use to ensure strong duality. Convexity, Slater's condition, etc. Okay, so that's it.